So today is the first day of Popple, and we're going to start off one of the two first sessions with a bit of a bang. So Jules Jacobs and Stephanie Balzer are going to present their work on deadlock type systems for deadlock freedom, and this is one of the distinguished papers at Popple. So we're going to really. How about now? Okay. Yeah. So, like I was saying, this is the first session of the first day of Popple, and we're going to start things off with a bit of excitement. So, Jules Jacobs and Stephanie Balzer are going to present their work on a type system for higher order leak and deadlock freedom. And I want to point out that this is one of the distinguished papers in the program. So, we're starting you off with some excitement, I think. Okay.
Hi, does that work? Great. Yeah, so I'm going to talk about memory leaks and deadlocks, in particular about a type system to prevent them that I worked on with Stephanie. She's here, so come talk to us afterward. So we are going to use linear types for that. And as you know, a prominent example of a language that uses linear types for memory management is Rust. So let me first show you how Rust uses types to manage memory. Here you see a function to compute the minimum of two numbers. First we allocate a vector on the heap. We put the numbers in the vector. We sort it, get the first element out, and return it. And the way Rust works is that each heap allocation has a unique owner, in this case v. And when the variable goes out of scope, the heap allocation gets deallocated. So you may think that this prevents memory leaks, but that's not exactly the case. Let me show you an example for that. For that we have to go to a more advanced type, the type arc of mutex of t. This is a shareable mutable reference to a value of type t. It's guarded by a lock, and it's reference counted. Furthermore, this t itself can be a mutex or contain a mutex, and we call this higher order by analogy to higher order functions. And since Rust has recursive types, we can even make a recursive type that goes through a mutex. Here, for example, we have a list where the tail of the list is mutable and it goes through a mutex. Well, this way you can create a memory leak. Here we create a list and then add a const cell where we point the tail of the const cell to the list itself. So we create a small reference, and that means that even after we drop x, the reference count is still 1 because the tail is still pointing to itself. And that means that the list is leaked. There's a second problem, which is deadlocks. Let me give you an example of that. Here we have a swap function. This swap function takes two mutexes. It acquires them both, swaps their contents, and then drops the lock guards to release the locks. Well, this function seems fine, but if we spawn two threads which do this swap operation in a different order, it can happen that both threads acquire the first lock and then they are both stuck on the second lock, so we have a deadlock. So the question we are trying to answer with this paper is, can we get leak and deadlock freedom by type checking? So in the paper we present a language Lambda Log, which is a lambda calculus with a linearly typed log API, in which any log that you have in scope can be safely acquired without creating deadlocks. Furthermore, it supports higher order logs, so we can store logs in logs even recursively, because we have recursive types. And still there are no memory leaks. And the type system ensures that by maintaining the invariant, that what we call the sharing topology remains acyclic. And we proved then in Coq that this means that there are no leaks and no deadlocks. In the second part of the paper, we present an extension in which we do allow this sharing topology to be cyclic by putting logs together in groups and then imposing a local log order within a group. But if you have two logs in different groups, you can still safely acquire them in any order. And for this language too, we prove leak and deadlock freedom. Okay, let's look at the main type. So we have this log of tau AB. But because this didn't fit on my slides, I redefined my LaTeX macro. So we're just going to do that. So this type is similar to arg of mutex of t, but it's linear. So in Rust, you can copy a mutex arbitrarily. We cannot do that. And these a and b's, they are booleans, and they indicate the obligations that we have for this reference. So if a is 1, it means that this reference has to deallocate the lock. If b is 1, it means that this reference has to release the lock. So let's now look at the API. The first function to create the lock is called new, and they start out with both obligations. So it means that this reference will have to deallocate the lock, and it has to release the lock. So initially the lock is locked, and it contains no value. So here we see a thread, T1, and if you call this new operation, we get a new lock in memory, which has reference count 1, and it has no value. The second operation that we have is fork. The first argument of fork is a lock on which we fork. The second argument is a closure, and it also returns the lock. So what fork does, it spawns a new thread that runs the closure, and it copies the lock that it gets as its first argument into the new thread, and it also returns it back to the parent thread. And as you see here, these obligations are split, so we can give some obligations to the child thread and some to the parent thread. So what that does is it allocates a new thread. In this case, we didn't share any obligations with the child thread. We kept them in the parent thread, and it increments the reference count. So we can do that multiple times. Okay, so then we have the functions release and acquire. So release takes an open lock and a value, and it puts it in the lock, and in return we discard that obligation. And acquire does the opposite. It takes a value out of the lock, and we get the obligation. So suppose T1 has a value v that it wants to put in the lock. We put it in, and as you see, we now lost the obligation to release the lock. Now T2 can acquire the lock. It can get access to the value temporarily and put it back. Okay, the last two operations are drop and wait. So what drop does is it just throws away the reference, but we can only do that when we have no obligations. So for example, T2 can do that, and T3 can do that. And then finally, we can call wait, and wait blocks until the reference count is 1, and then gets the value out. So you see that here. So this is our base API, and it turns out that this is all deadlock free. For example, now we can write this swap function that we have seen before, and now it's safe to acquire both locks because the invariant of the type system guarantees that L1 and L2 will not be locked in a different order in a different thread. Furthermore, we can do promises or futures or fork join parallelism. So what we do is we create a new lock, we fork on the lock, we give the obligation to release the lock to the child thread and to wait on the lock to the main thread. And that way we can run a computation in parallel and eventually get a value in the main thread. So this obligation to fulfill these promises, they cannot be discarded. So this ensures that everything will eventually happen. Okay, so let's now talk about this higher order aspect, which allows you to store locks in locks. So if you have a lock where the payload type is itself a lock, you can put another lock in that. And that is all still leak free. So that means that the type system ensures that there is no reference cycle at the end of the day. And it can happen that another thread acquires this lock to get the lock L2 out. So the locks can now travel between threads. Because we have recursive types, we can do recursive mutable data structures. For example, a mutable tree, that is a lock which stores either a leaf or a pair of trees and a value. It turns out that we can also encode session type channels as a library, even recursive ones. Because our type system is deadlock and leak free, it also means that it also holds for this library. Lastly, we can do shared sessions by putting a session in a lock, And that means that someone can acquire the lock, get the session out, do some interactions, and put it back. And then another thread can take its turn. So we have seen that in this language, we can duplicate one lock on fork. So would it be possible to allow duplicating two? So here we imagine that we have some API like that where we put a tuple into the fork and we get two locks in both sides. Well, as we have seen, that's not safe because the main thread and the child thread could acquire them in a different order and then create a deadlock, or they could store them into each other and create a reference cycle. But actually, if we impose some additional restrictions, then it is safe. So what we have to do is we have to make acquire and wait follow a lock order, and we have to prevent threads from storing them into each other. And we do that with the following type. So here we have it's the same as the previous type, except you have multiple entries. And so it's like a tuple of locks in a way. And we are going to ensure that you can only acquire the locks from left to right. And you can also wait only in a certain order, and we will see the exact restriction later. So to this tuple, we can add and remove locks dynamically. And this means that this tuple is only a local view into the complete order on the lock group, because it's possible that you put a lock in the tuple, but someone else doesn't know about that, if someone else already had a reference to the lock group. So here is the lock group API. So the first two are just to create and destroy an empty lock group. And then all the operations that we had before, except fork, all the operations get an index, which indicates where in this tuple we operate. So for example, for the new operation, it takes an index k, and that means that it will insert a new lock at position k into the tuple. And the same for drop and release, and acquire and wait. So for acquire and wait, there is an additional restriction, namely, for acquire, you see here this red 0, which means that all the locks that come after the lock that we want to acquire, they have to have lower index 0, which means that they are not already acquired. And for wait, we also have restrictions. And there you have the restriction that nothing is acquired. And all the locks to the right, we do have the obligation to wait on those. And it turns out that these restrictions are exactly enough to ensure deadlock freedom. And fork can distribute the obligations as the fork did before, but now it's just for point-wise for each entry. Okay, so now we have another variation of swap, and this time within a lock group. So now we indicate by the index which lock we want to acquire, but the type system now ensures that we do acquire the zeroed lock first, and then the lock with index 1. But there is no restriction, acquisition order restriction between two lock groups. So if you have two lock group references, you are free to acquire them in any order. And it's a common misconception that you can do that with partial lock orders, where you don't have a total order on the locks, but a partial order. But actually it turns out that's not true, because the more partial you make your orders, the worse it gets. You can only write fewer programs, not more programs. So an example of what we can do with that is Dijkstra's dining philosophers. So that's a problem where you have a philosopher sitting around a table, and they each try to acquire forks left and right of them. And the problem there is that it's sitting in a cycle. So if all the philosophers acquire the lock on the right simultaneously, and then try to acquire the lock on the left, then we have a deadlock. So we can encode this example in our language, but the type system forces us to choose one philosopher who acquires the locks in a different order, which then prevents the deadlock. And so what happens is that each philosopher has a lock group of size 2. So actually all the locks are in the same lock group, but each philosopher only knows about 2 of them. And then the order in this tuple enforces this acquisition order. And actually, because we have this ability to add new locks and spawn new threads, we can even grow the table dynamically. So we can go from 3 to 4, and we can even add new cycles in the table. And in the paper, we have an example a recursive example which grows this in a fractal manner, which creates many cycles. And still it's deadlock free, of course. So let's look at how we state the theorem that things are leak and deadlock free. So we use a small step semantics on a configuration, which is a set of threads and locks. And we are going to treat locks and threads in the same way. So we put them in the same set. And we define this relation waits for, where X is an element of the configuration and Y is an element of the configuration, which can each be threads or locks. We say that X waits for Y if X is a thread and it's currently trying to do a lock operation on Y. And we say that X waits for Y if Y has a reference to lock X. And using this relation, we can define two notions. The first is reachable, which you should think about reachability in the terms of garbage collection. So we say that X is reachable if it transitively waits for a Y that can step. So Y has to be a thread then. Similarly, we define the notion of deadlock for a subset of our configuration. We say that that's in a deadlock if nothing in the set can step and nothing is waiting for something outside of the set. So then we have a few theorems about that. The first theorem is that it's equivalent to say that everything in the configuration is reachable and that there are no non-empty deadlocks. And we prove, of course, that well-typed programs do not leak and deadlock in this sense. And a corollary of that is that we have global progress, that if the configuration is non-empty, then the configuration can step. So this means that as long as there's a thread in the configuration, then it can step. But also, as long as there are locks in the configuration, suppose there are only locks in the configuration, this theorem would say that it steps. But actually, locks alone can, of course, not step. So this theorem also gives you that at the end of the day, all your locks are deallocated. So we have proved this all in Coq, of course. And an insight from this is that leak and deadlock freedom are related, because here you see on the one hand we have this notion reachable, which sounds like leak freedom, and on the other hand we have this notion deadlock, but if you formulate them in this way, then they become completely equivalent. So let me just mention some related work. So there is a lot of related work in this area, in session types, in pi calculus. So the most important one is the class work by Pedro Roca and Luis Caires. And they have an upcoming paper in ESOP, which if you like this work, you will also like that. You have client-server sessions by Kian and Carlos and Birkedal. You have usages and obligations by Kobayashi. There is a lot of work on that. You have priorities, and you have manifest sharing by Stephanie, my co-author. But there is, of course, a lot of other work on session types, and this is all very much related to what we do here. So some future work that we want to work on is to support DAG-shaped mutable data structures, because our invariant actually ensures that your data structures remain trees. So it's possible that a node in your data structure has multiple owners from multiple threads, so it's not quite single ownership, but we cannot support DAGs. Because if you have a path in a DAG that converges again, then somehow you could go via both paths and create a deadlock by acquiring the same lock twice, or something like that. We also want to look into supporting RC and refcell. So here we support arc mutex, but we think something different is needed for RC refcell. And more generally, we want to integrate this with the features that make Rust nice, such as borrowing and the ability to write unsafe code, and in particular, a kind of system where you can prove something about your unsafe code, such that if you link it with your safe code, that you still get all the nice theorems. So we don't have something like that yet. So, to conclude, Rust is a practical memory-safe language without GC. So the question that I want to leave you with is, can a practical language be leak and deadlock free? So, of course, this work does not completely answer that, but I hope to at least have convinced you that it might be possible and that it's worth trying to do. And that a promising direction is to generalize from single ownership to a more general notion of sharing topology. Yeah, I hope you read our paper. This reviewer had something positive to say about that. So I think the paper is quite readable. So, and of course, you can also come talk to us if there's any questions you have. Thank you.
Okay, so we have a few minutes for questions. And if you can ask your question, I'll bring the microphone to you. One sec. Also, could you give your name and affiliation?
Hi there, I'm Max, University of Washington. Great talk, thanks for giving it. You mentioned DAG-safe data structures as a potential future challenge problem. What about cyclic data structures? Especially, I find the allocation problem very interesting. You have weak pointers and all this stuff. So can you comment on that, please?
Yeah, I think cyclic data structures is even more difficult. So, yeah, there has been some previous work in Rust about that. It's called ghost cell. So I think that's an interesting approach. I think it's kind of hard to, I don't know whether you can integrate something like that with this so that you can create cyclic references within true mutexes, but it would be interesting to explore.
All right, does anyone else have a question? Yes.
Hello, I'm Tachio. Could you clarify the difference with the work by Kobayashi?
Yeah, so I think there are two important differences. So one difference is, I think here this notion of sharing is very important. And I think another difference is that this notion of log order, so there's a lot of work by Kobayashi, so it depends on what you're talking about. So so log orders are a little bit different in the sense that you can go both up and down in a log order, whereas with usages and obligations, maybe you can only go forward in a certain sense, but I think it's kind of difficult to pin down the exact relationship. Yes. So we use a lambda calculus, but that difference is maybe less essential.
Hello, I'm Jed Galliini from the University of Cambridge. So I have a question. So in the typing rules, you need to do like a split. So you need to find,
Yeah.
A, B, that you XOR them and you get the right thing. So my question is there an efficient type inference algorithm for figuring out what the split is? There probably should be. And is there a way to actually do this check at runtime? So maybe as like, a sanitizer for like debug mode. So you have a language that doesn't check this, but the locks are annotated with something to make them check this, and you have special lock group type.
Yeah, I have not really looked into doing type inference for it, but I could imagine something like, so we're talking only about Booleans, so you might be able to set up some kind of constraint system between Booleans, and then see if that has a solution. I don't know if that will always have a unique solution. And about the second question, doing it at runtime, I guess that should be possible, because you could check at runtime, for example, if you throw away your reference, if you call drop, for example, and yeah, you could maybe look at the reference count and see if that still works. But I think it's difficult at the end of the day then to assign blame to who did something wrong.
think we have time for, sorry, I think we have time for one more question if anyone wants to ask it.
Hi, I'm Mark from UCSD. My question is, you say you have support for something like ArcMutex, and
Yep.
you want to also have support for something like RCRefcell. What will that get you above just ArcMutex? What new powers will it have?
Okay, so the main problem here is that in certain cases here, we have to spawn a thread to do something with something that's in the mutex, which is not something that you want to do for RCRefcell. So maybe we can do something like fork, but which doesn't actually spawn a thread or something like that, but we don't know yet.
Okay. Okay, could we have another round of applause?